What I have before me now is a block diagram for the homework assignment, which will examine the bit error rate performance of an optical communication system using on-off keying, or what's also known as intensity modulation with direct detection. We'll be examining the effect of noise and the effect of filtering and pulse shape on system performance. In the homework assignment, you're asked to generate several curves for bit error rate versus the transmitted power, or equivalently the received power. In this system, there are three types of noise that we're going to be examining. There is the ASC noise, or the amplified spontaneous emission from the use of an optical amplifier. There is also the noise added in the electrical to optical conversion by the PINN, the photodetection process. When using a PIN diode, you will introduce both thermal noise and shot noise. So the three noise types are ASE, shot noise, and thermal noise. Another thing that you're asked to do is to examine the impact of transmission rate and filtering on the communications link. We'll consider both 10 gigabits and 40 gigabits per second transmissions. We will look at three different kinds of pulse shapes. So here we have P of T representing the pulse shapes. We'll consider first a rectangular non-return to zero pulse shape. We'll also examine rectangular return to zero with 50% duty cycle. We're halfway through the bit interval. The rectangle transitions to zero. Since RZ rectangular pulses are half as wide in the time domain as the NRZ rectangular pulse, the RZ pulse will occupy twice the bandwidth in the frequency domain. The third filter we'll be using is the root raised cosine, or RRC, with a 30% roll-off factor. The root raised cosine is a very practical pulse that allows us to trade off bandwidth expansion against robustness to timing errors, for instance, robustness to jitter. We will include one fixed optical filter, and that is present mostly to filter the very wideband ASE noise. We will consider two types of electrical filter. The first, the match filter, and the second, a Bessel filter. The match filter will of course change as we change the pulse shapes. The match filter shape will also change. Let's return now to the block for the homework assignment. The first element is a laser source. We use an ideal laser source with no relative intensity noise and no phase noise. So it's a perfect monochromatic source. Next, we have an external modulator that accomplishes the electrical to optical conversion. We can use a finite extinction ratio for the external modulator, although I don't think it will be very important for the levels that we're considering in this homework assignment. Following the external modulator, we have a virtual combination of an ideal fiber and an ideal amplifier with gain G. These two elements taken together are essentially an all-pass filter. We assume that any losses in the fiber have been exactly compensated by the gain G. The noise properties of the amplifier are modeled by the spontaneous emission block. In this case, it's an additive white Gaussian noise. The optical filter that follows the ASC is used to limit the bandwidth of the ASC noise. Following the optical filter, we have the detection process where we accomplish the optical to electrical conversion. As we mentioned earlier, the photodetector introduces thermal and shot noise. In the electrical domain, we include an electrical filter to limit the shot noise and thermal noise. Next, we sample our signal at the bit rate. Note that we'll be using 8 times oversampling in the simulation. Finally, we threshold the sample to decide whether a 0 or a 1 has been transmitted. When running simulations, one of the most useful tools you have for validating your results is to turn towards theoretical results. There will be certain regimes of operation where you expect your simulation to closely reflect theoretical results. So one of the first things we'll ask you to do is to plot the theoretical curves. Even the theoretical curves you could make mistakes on in your simulations if your normalizations of noise and other aspects of the simulation are not right. So what we're also going to do is validating the theoretical curves. So by doing that, we'll just pick a point and we'll calculate roughly what we think that point should be. When we plot our theoretical curve, we'll see if we do indeed fall to that point. So let's start with an exercise of validating the thermal noise. In this case, in the homework assignment, we're going to be looking at bit error rate at 10 to the minus 4. So I can start with the on-off keying. We know that the bit error rate is equal to 1/2 the error function complementary of the Q factor divided by the square root of 2. So if we want to achieve bit error rate equal 10 to the minus 4, that would mean that we would need a Q factor, which was equal to the error function complementary inverse of 2 times 10 to the minus 4 times the square root of 2, or 3.719. So now we can turn to an approximation for thermal noise limit from Agrawal in the excerpts I provided you from his book on page 165, equation 4.618. I'll repeat for you here. It says that the received power is approximately equal to Q times the thermal noise variance divided by RD in the thermal noise limit. In our simulator, our homework assignment, we're given that RD is equal to 1.25, and at 10 gigabits per second, we can find that the thermal noise variance should be equal to about 1 microampere. So that would give us a way of calculating what we believe the received power should be. 3.719, 1 microampere divided by 1.25 amperes per watt gives us 0.003 milliwatts, or minus 25.3 dBm. So now I'll go and I'll plot in MATLAB my theoretical curve using the equations we learned in class, and I'll check at 10 to the minus 4. I have something like minus 25 dBm. And so this matches well, very well, good point at 10 to the minus 4 implies that my theoretical curve is accurate. Once again, we're going to be validating some theoretical curves. In this case, we're going to be looking where we believe ASE noise is dominating, and again, to look at the 10 to the minus 4 bit error rate point. So we'll start with a few approximations from the ASE noise limit. We'll say that the variance for a 0 transmitted, which we'll call the spontaneous noise. There'll also be thermal noise and shot noise, but we'll assume that we're ASE noise limited. And the noise variance under the logical 1 would be the sum of the spontaneous variance and also the signal spontaneous variance. Now we're going to calculate our Q factor, and our Q factor by definition is I1 minus I0, sigma 0 plus sigma 1. And for high extinction ratio, we're going to neglect I0. I1 will be much greater than I0, so that's the first approximation for high extinction ratio. Next, I'm going to consider the relative values of sigma 0 and sigma 1. I'm going to assume that when we're working at 10 to the minus 4 that the transmit power will be higher than the ASC power, probably quite a bit, and I'm going to make the approximation that the spontaneous variance is much smaller than the signal spontaneous variance. And if this is the case, then I'm going to say that sigma 0 plus sigma 1 is approximately just sigma signal spontaneous. In other words, I'm neglecting the spontaneous noise. With these approximations, we get to the Q factor is approximately equal to I1 over sigma 1, or we'll call that our signal current, divided by the variance of the signal spontaneous contribution. Now we learned in class that this variance of the signal spontaneous contribution is given by 4 times the signal power, or current, excuse me, and the ASE current divided by the optical bandwidth multiplied by the electrical bandwidth. So we can simplify that a little bit. It's the signal current squared, optical bandwidth, 4 times the signal current, ASE current, electrical bandwidth, and of course that's just 1/2 square root of the signal current divided by the ASE current, and the square root of VO over BE. So what can we do now to try and find what our results will be? Well, we'll start out by saying that the signal current is the optical signal received power times the responsivity RD, the ASE current. Well, there's a couple ways we can look at this. We had an equation we saw in class that looked something like this, but another way of looking is saying it's simply the ASE power times RD, and a similar way for the signal. Same thing applies to ASC. And in this homework assignment, we're going to be given that the ASC power specified in terms of a power spectral density at a reference bandwidth. So we'll call it the PSD of the ASC at a reference bandwidth. And so, of course, we're going to have to multiply that by the optical bandwidth in order to get the PSD in the the ASC power within the optical bandwidth times RD. Fine. So next, we can go back to our equation for Q, say it's about 1/2, and now what I have is the received power due to signal divided by the PSD of the ASC, and I'm going to get B bandwidth of the reference bandwidth divided by the electrical bandwidth. And in the homework, we're given that the PSD of the ASC is minus 35 dBm in a reference bandwidth of 0.1 nanometers, or the equivalent of 12.6 gigahertz. So now we can calculate what received power we think that we'll need due to the signal. So the received signal power should be 4Q squared, the electrical bandwidth, divided by the reference bandwidth equal to the signal received power, power spectral density of the ASE. And of course, in our case, it's 3.719 for the Q factor that we're looking for 10 to the minus 4. The electrical bandwidth of NRZ would be 10 gigahertz divided by 12.6 gigahertz. This leads to 16.6 dB, so that the power of the signal, received power of the signal in dBm should be equal to the power spectral density of the ASE, which is already in dBm, plus 16.6 dB, which gives us about minus 18.6 dBm. So now if I go into my generation of the theoretical curve for the ASE noise at 10 gigabits per second, I can see that at 10 to the minus 4, I have something just under minus 20 dBm, which corresponds pretty well to my calculated value of minus 18.6 dBm. So again, we have a good validation at 10 to the minus 4, which makes us believe that our plot of the theoretical curve is accurate. So now I'd like to discuss the proper normalization of the filters and the signals used in your simulator. Let's start with the filters. We have an optical filter, we have an electrical filter, and a typical means of normalizing a filter is to use what we call the unity gain normalization, which basically says that we take the frequency response at DC for our filter, and we set the frequency response at DC equal to 1. The next normalization that we're interested in is what to do with our pulse shape. And in order to understand what's going on here, let's think about the model that we have for our PIN. For our PIN, we're modeling it as a square law device, so the signal is squared, and then afterwards there's noise added, either shot noise or both shot noise and thermal noise. And we're also saying that the current is equal to RD, the responsivity, times the optical power. What this is really saying is that there's a proportionality which exists between the average optical power into the photodiode and the average electrical power generated by the photodiode, and that RD, the responsivity, gives this figure of proportionality. So we want to make sure to respect that. Well, first of all, our pulse shape P of t is going to be changed by the impulse response of our optical filter, so that what's going to be input to our PIN is actually the convolution of P of t with the impulse response of the optical filter. And if we look in the electrical domain, we've said that this is a square law device, right? So what we're going to have here is P of t convolved with H0 of t squared. So if there was an optical filter and our pulse shape was an RZ, our RZ would be equal to 1, and when we square it equal to 1, and there would be no ambiguity in our manipulations. However, in your simulations, we're going to have several pulse shapes for P of t, and of course they're all going to be changed to a greater or lesser degree by the optical filter. For instance, if the bit rate is 40 gigabits per second and the optical filter is 50 gigahertz wide, there'll be some changes in the spectrum due to the filtering. Okay, so how do we make sure that our model is well reflected in our simulator? So again, R of D is the proportionality constant between the electrical and the optical power. So if we take our pulse shape, which is at the input on the optical side, which is P of t convolved with H0 of t, and we look at the average power, it's going to be different from the average power when we look at the squared signal. So what I'm going to do is introduce a normalization to P of t, and the normalization I'm going to choose is such that these, for the given shape P of t, these two quantities are the same. So I'm going to normalize it so that if I take the power of either of them, they give the same results. Okay, so if you don't do the normalization that I mentioned here, you're going to get a discrepancy in your bit error rate curves. Here is a simulation which uses 40 gigabits per second. It's an NRZ shape. In this case, we're not including ASC, it's simply shot in thermal noise. And on the left here, I've made a good normalization, and I can see that when I run my Monte Carlo simulations in blue, they're exactly matching my theoretical ones because I've done the right normalization. In the second case, I'm getting a penalty between the theoretical curve and my simulations with a Monte Carlo. And the reason I'm getting this penalty is I have not done the good normalization. So let's look what happens. On the left here, we have improper scaling. And what that means is that in the optical domain in red here, we have a certain shape, and this is the NRZ at 40 gigabits, so it's been all of its sidebands have been cut off due to the optical filtering. When we go into the square loss device, we get the impulse response, or excuse me, the frequency response you see in the blue curve. And you can see that it's sort of been dissipated by being squared, and this is the reason for the discrepancy. If we look at the proper scaling, when we do proper scaling, the pulse shape has been adjusted so that in the electrical domain we see the blue shape, in the optical domain we have the red shape, and their powers are the same in the two cases. I'd like to discuss now the thresholding, which is the last operation that we do in our simulator. And we saw in class that the optimal threshold can be given by the expression here, where we, based on the noise of the marks and spaces and the current of the marks and space. This is accurate in Gaussian noise and under a number of assumptions. What you'll find in your simulations is if you use this optimal threshold, it's not really optimal. And in fact, if you were to look for a threshold that was optimized numerically, that you would get a better bit error rate. And again, it's because of some of the assumptions made in the derivation of this optimal threshold. So what I suggest that we can do instead is that we fix the power, and then we start with eta, the threshold equaling to this sort of default value, and we calculate the bit error rate. Then we begin iterating. We iterate because we change the initial threshold, and we examine both sides of values around this initial value. And for each one, we calculate the bit error rate. And Once we have examined a number of thresholds, we simply find which threshold corresponds to the minimum bit error rate, and we use that. And that is a numerically optimized threshold. And we'll do this for each one of the powers. And this will be important for you to get accurate results throughout, but especially when you're doing your validation. I think you'll see a difference when you use the numerically optimized threshold and compare that with your results against the theoretical. Finally, I'd like to talk to you about how we can validate our simulations by comparing theoretical results with simulation. A couple of points. One, simulations should not be better than theory. If you find out that your simulator is giving you much better performance than is predicted by theory, then you've probably got an error. We simulate in order to capture effects which are not captured in the theory and which worsen performance. Secondly, when you're trying to validate your simulation results, you should think about when we have regimes of operation where we expect theory and simulation to match. Okay, where is this going to be? This is going to be when the channel bandwidth is much greater than the signal bandwidth. So the signal has lots of space, and in this case we expect that the theoretical calculations we've made will be accurate. So that's something that you can check. And then we would expect deviations when this is not true. In fact, that's why we do simulations, to find out what these variations are. Another tool that you can use is the Q-factor prediction of bit error rate. The relationship between the bit error rate and the Q-factor, which we've seen, is valid in the case when the noise is Gaussian. So one thing you can do is calculate the Q-factor, and then based on that Q-factor, calculate what the bit error rate should be, and see if that deviates from your simulation results. If it deviates from your simulation results, you would conclude that the Gaussian approximation is not valid. For instance, if an intersymbol interference was present.